Hey everyone, and welcome. Today, we are diving deep into the secret code that runs our world. We're going to be decoding the invisible instructions that power everything from your phone's photo library to the entire global financial market. So, let's jump right in.
I mean, really think about that for a second. You've got maybe 20,000 photos on your phone. How on earth does it sift through that, a whole digital lifetime of memories, and find the one you're looking for instantly? It seems kind of like magic, right? Well, the secret sauce, the magic trick, is something called algorithms. And look, I know that sounds like a complicated, scary word, but it's not. An algorithm is just a recipe. That's it. A specific, step-by-step set of instructions that a computer follows to get something done. And they are the engine behind almost every piece of tech we use every single day. But, before we can start cooking up a complex recipe, we have to understand the basic ingredients. We need to get to know the fundamental Lego blocks that every single program is built from. First up, the simplest and maybe most important block, the variable. Just think of it as a labeled box. That's all it is. You give the box a name, like my age, and then you put one piece of info inside, like the number 30. It's how a program remembers stuff. Super simple, but absolutely crucial.
So variables are our ingredients, then statements are the individual steps in our recipe. Each statement is one single command. Things like create a box named age, or put the number 30 inside that box. A whole computer program is really just a long sequence of these little commands.
Okay, but what if you have like a ton of similar boxes? Say a list of 100 different ages. That's where an array is a lifesaver. An array is basically just a big shelf with numbered slots. It lets us organize a whole sequence of similar items, and the best part is we can instantly grab any one of them just by knowing its number on the shelf. All right, we've got our building blocks. Now, let's tackle a classic, and I mean classic, computer science problem. Imagine you're handed a massive, completely jumbled up list of items, a total mess. How do you get it in order? This is the fundamental challenge of sorting. So one way you could do this is called selection sort. And honestly, it's probably how you do it yourself if you were sorting a hand of playing cards. You just scan through the whole messy pile, find the absolute smallest thing, and you stick it at the very beginning. Then you do it again for the rest of the pile. And again. And again. It makes sense, it's intuitive, but as we're about to see, simple does not always mean fast.
Okay, let's watch this thing work. In the very first pass, the algorithm looks at all 12 letters and says, yep, A is the smallest. So it swaps A with S at the front. Now, see that? The A is locked in. It's done. Next, it looks at the remaining 11 letters, finds the first E, and swaps that into the second spot. You can see how it just slowly, methodically, one by one, builds up the sorted part of the list from left to right.
But there is a much more clever way to do this. It's called merge sort. And this is just a beautiful example of a really powerful computer science strategy called divide and conquer. So instead of trying to wrestle with the whole big list at once, merge sort just splits it in half. Then it splits those halves in half. It keeps breaking the problem down into smaller and smaller pieces until all it has is a bunch of tiny lists with only one item in them. And a list with one item is already sorted, right? Then comes the clever part. It starts merging those tiny sorted lists back together into bigger sorted lists until, bam, the whole thing is perfectly in order. It's just an elegant way to turn one huge hard problem into a bunch of tiny easy ones. So why do we care? Who cares which method we use? Well, for a tiny list, it doesn't matter. But as that list gets bigger, the difference is absolutely staggering. The time it takes for selection sort to run grows exponentially, what we call n squared. That means if you double the list, the time it takes quadruples. Merge sort, on the other hand, grows way slower, n log n. For a list of 1,000,000 items, we are literally talking about the difference between waiting a few seconds and waiting a few days. The algorithm you choose is everything. So we've brought order to the chaos. Awesome. Now what do we do with our nice, tidy, sorted list? Well, a whole new universe of possibilities opens up, and it starts with being able to find things ridiculously fast. To do this, programmers use a structure they call a symbol table. Don't let the fancy name fool you, though. You use this idea all the time. Just think of it like a regular dictionary. It's a system for storing pairs of information. You have a unique key, like a word, and it points to a value, like its definition. This simple idea powers pretty much everything. So let's imagine we have our big list of numbers, and thanks to an awesome algorithm like merge sort, it's in perfect order. Now, what is the absolute most efficient way to find one specific number in that list? I mean, you could start at the beginning and check every single one,
But we can do so much better than that.
The answer is a truly powerful algorithm called binary search. So here's our sorted list of numbers, and let's pretend we're on the hunt for the number 77.
Now this is where the magic really happens. Instead of starting at the beginning, binary search jumps right into the middle of the list. The middle number here is 48. Now, because we know the list is sorted, and we know 77 is bigger than 48, we know our number cannot possibly be in the entire first half of the list. So what do? We just throw it away. In one step, we've cut our problem in half. Then we do it again on the half that's left. The new middle is 68, still too small, so we throw that half away. And on our third try, we land right on 77. Just 3 checks to find our number in a list of 16. It's incredibly efficient.
Okay, so these ideas, sorting and searching, they might seem a little abstract, right? But I promise you, these are the invisible engines running constantly, quietly, in the background of your daily life.
That symbol table concept, combined with a super fast search, it is everywhere. When a search engine finds a web page, that's a symbol table. When your computer turns a web address, like google.com, into a numerical IP address, that's a symbol table. Your social media feed, looking up your bank balance, even your spell checker, they are all built on this fundamental idea of linking a key to a value and finding it in a flash.
And this leads to this really cool, powerful idea in computer science called reduction. All it means is that you can use an algorithm you developed for one problem to solve a totally different new problem. For instance, how would you find out if there are any duplicate numbers in a big list? Well, you could check every number against every other number, or you could just sort the list first. Once it's sorted, any duplicates will be right next to each other. Suddenly, a new problem is super easy to solve using our old tool.
And we can take these same building blocks even further to model much more complex stuff. Using things called symbol graphs, we can map out all the connections between things, like airports connected by flights or actors connected by the movies they've been in, and then we can use algorithms to find the shortest path between any 2 points, whether that's the best flight plan or, figuring out how many movies it takes to connect any actor to Kevin Bacon. And at the end of the day, it all comes back to this one thing: efficiency. This chart says everything you need to know. A simple brute force approach like our selection sort becomes completely useless for large amounts of data. The bar just goes to the moon. But an efficient n-log-n algorithm like merge sort or binary search, it stays fast, practical, and it's what makes our modern digital world even possible.
So think about that for a second. We went on a whole journey here. We started with the simplest ideas imaginable, a labeled box for info, a list of instructions, and from those tiny pieces, we built our way all the way up to the sophisticated logic that powers global networks and massive databases.
And that really is the heart of it all. Our world runs on these clever recipes, which just makes you stop and wonder, right? What other invisible algorithms, what other elegant sets of instructions are quietly humming in the background right now, shaping our reality in ways we haven't even noticed yet?